So again, let's go to the so-called Kelvin equation, which relates relative pressure, the pressure versus the saturation pressure, relative pressure, and R for radius for the pore, right? We are dealing with porous ceramic material, radius for the pore, and it's very simple. Relative pressure and the radius pore. From here, we can back calculate. If we have a relative pressure number, and if we know the system we are dealing with, which means in principle we know cosine theta, we know VL, we know gamma LV, we can back calculate the corresponding pore size, in this case pore radius, to be this one. Make sense? Okay. And now let's plug in the number. For liquid nitrogen, typically we assume pretty good wetting. Theta goes to 0, cosine theta is 1, okay. And surface tension, people have measured surface tension. It's in the unit of Newton per centimeter per meter. Surface tension, okay, between liquid nitrogen and the nitrogen gas. Okay, the other one is liquid molar volume, which means 1 molar of liquid nitrogen. What's the volume? Of course, at certain temperature, 77 K. Okay, so once we plug these numbers into, well, into this equation, right? Cosine theta 1, VL, we have it, and the gamma LV, we have it, R, we have it, T, 77. So essentially, we would have something like this. R, we will plug the number in and simplify it. We would have R, the radius would be minus 0.944 divided by natural log of the relative pressure. Of course, it will be in the unit of nanometer. Okay, it will be in the unit of nanometer. And sometimes we can convert from natural log to log with a base of 10. Right, that's essentially what we did. And now we can link the relative pressure and the so-called cumulative pore volume from VAD, from the adsorbed gas volume. Again, this is our adsorption, desorption isotherm, right? Isotherm, you get it at the same temperature, in this case 77 K. The y-axis would be the adsorbed gas volume converted back to STP condition. The horizontal axis would be relative pressure from vacuum all the way to saturation. Okay, and we start from 0 going up, monolayer coverage, multi-layer coverage, going up, and reach saturation and go back down. Adsorption going up, desorption going down. Make sense? And we have hysteresis loop. This means we have capillary condensation. The gas being filling the pore, multi-layer, is behaving like a liquid. Okay. And then for each of the points on here, we can get adsorbed gas volume and the relative pressure. From the relative pressure, we can get the equivalent what? Equivalent from the relative pressure. Here, I only need relative pressure, right? I can get an equivalent radius, pore size, and from the VAD, I can get the amount of gas that is needed to fill in the pore up to that point. Make sense? And initially, you have 0 gas to fill in the pores. When the pores are tiny, I don't need any gas. And when the pores are getting larger and larger, I need more and more gas to fill in the pore. Okay? So for any relative pressure, I, which means a specific point on this curve, the PI for a specific point on this curve, the VCI, C for cumulative pore volume, I corresponding to that point, give the cumulative pore volume up to size Ri. Of course, R for radius, I for that specific point, Ri is get from here. Make sense? Okay. And of course, naturally, as what we learned, within the material, there will be regions that we have narrower pores, smaller pores. And there will also be regions that we have larger pores or wider pores. Make sense? Just and assume they are connected. Open pores are connected. And if we plot the sets of data of so calculated VCI for cumulative pore volume corresponding to that specific eye point versus R for radius for that eye point. Both these are calculated, okay, using the P over P0 and the VAD data, give the cumulative pore volume plot, okay. And then if we do differential of that cumulative plot, we would get the so-called pore size distribution that you sometimes see it. Also, we call it PSD, pore size distribution. And the pore size distribution is we do differential with respect to radius. The cumulative pore volume with respect to radius. And of course, in this case, we would have hysteresis. Why hysteresis? Well, when we go to this pressure, we fill up some pores. But if we want to fill up a little bit more, you can imagine we fill up the smaller pores, but we want to fill up larger pores. We have to go step up the pressure a little bit, which means there will be some delay in the adsorption process. If I want to fill up this one, and quite often here it got filled up first, makes sense? And if I want to fill up here, this guy is already filled up. What do I have to do? I have to push it. That's the origin of this hysteresis. I have to push it a little bit to push the liquid from here to here to fill in order to fill up. That's called delay in the adsorption. On the other hand, for desorption, it's the other way. Okay. So that's where the hysteresis come from for adsorption, desorption with condensation. So here I'm going to show some example plots for the so-called pore size distribution and the so-called cumulative pore volume plot. I'm showing the data that I generated several years ago, okay, when I was younger, your age. And this is the so-called cumulative pore volume. Cumulative pore volume versus pore diameter. Where do I get this one? From so-called Kelvin equation. I have the relative pressure. I can calculate this corresponding radius. Where do I get this cumulative pore volume? I got it from the VAD, the adsorbed gas corresponding to pressure. The adsorbed gas under STP, I can convert it back to the cumulative pore volume. And then I got something like this, which means the majority of my pore volume are for pores larger than what? At least larger than 10 nanometer in radius. Make sense? Or probably around the 20. That's where the majority of it. The amount of total pore contributing to the volume less than 10 nanometer is negligible, very small, less than 5–10%. Okay, this one, remember, has a unit of centimeter cube per gram. The pore volume, cumulative pore volume, is for amount of powder you're dealing with. It has to be normalized, right? If you are dealing 1 gram versus 100 gram, the total pore volume will be different. But when we normalize, we can compare. Make sense? And then for this plot, if we are going to do differential, where the peak will be mathematically. If we are going to do differential of the cumulative pore volume VC versus dVC over dR, where would be the peak would be the highest slope? Somewhere here, right? Okay. So that's what we got. The so-called pore volume frequency. It has a strange unit of this guy over this guy. Make sense? It's specific pore volume, again, divided by pore size. And our peak corresponds to around between 10 to 20 to 30. Make sense? That's our highest frequency. Put it another way. Highest, which corresponds to the steepest slope. And when it's small, the slope is low, right? Here, slope is low. And when it's really large, the slope drops to 0. Makes sense? That's what you learned in mathematics. Makes sense? Okay. So that just shows the majority of the pores within this material is roughly 10 to 20, 30 nanometer. Okay? And if you remember the ICM and TM image, they correspond. The particles are 10 nanometer and the pores in between them are roughly 10 nanometer. Makes sense? Okay.